enjoyed your lunch. My name is Cristian Teodorescu. I will present the next session. And the next speaker will be Joseph Fontcumberta. We'll speak about electron transport and plasmonic response of metallic oxides. So please be welcome. Yeah, it's needed for the Zoom session.
All right. Good afternoon to this. Welcome to this afternoon session. My name is Josep Fontcumberta. I'm coming to the Materials Science Institute in Barcelona. And today I would like to comment a bit on correlated matter, properties of correlated metals. And in particular, I would like to comment on the transport electronic properties of some metallic oxides, which is quite different from what we have learned this morning. This morning we learned a lot of things about dielectrics, basically. I'm now going to metallic oxides. And the message of my presentation is summarized in this slide that you see here. As you know, in correlated materials, in particular in correlated metal oxides, it is typically understood that electrons doesn't have the free electron mass, but have a larger mass, which is dictated by the correlations among electrons. This larger mass, or these electrons which are dressed by the cloud of other electrons, are called the dress electrons, and supposedly this is the reason why these carriers have this higher mass. What I'm going to try to convince you that is that this scheme that is so far well accepted may not be complete. I'm going to push for the idea that electrons in a metallic oxide, in fact, move in a lattice of constituted by ions, and the ions themselves, they get are trapping the carrier, and this cloud of electrons surrounded by distortion of the lattice is what dresses really the electrons rather than the interaction with the neighboring electrons. So this is a very different view of the standard view, which is here. I'm going to show that that could be a better explanation. And anyhow, I'm going to show that these dress electrons make the electrons heavier. And as a consequence, these metals, which have a huge number of electrons, 10 to 23 electrons cubic centimeters, so really are intrinsic metals, have the plasma transition at infrared rather than the visible or at ultraviolet, because the mass of the carrier is very large. This is the output or the summary of my presentation. Now I'm going to go into the details. I'm going to talk about oxides, metallic oxides, and I'm going to have interest in metallic and transparent oxides. What is a transparent oxide? Well, the name speaks by itself. You know, in a standard metal, you have, this is the reflectivity of a metal, this is the energy of the light coming onto the metal. Typically you have a high reflectivity and then at some point a drop of reflectivity, and this drop of reflectivity is called the plasma frequency. In a normal metal, this plasma frequency is ultraviolet, and this is the case of aluminum, silver, gold, and so on. So the metals in the visible are fully reflective, and this is why they are bright. And we use mirrors made out of metals. So this is a conventional metal. Are visible, are transparent at the visible, are reflecting at the visible, you see, because the reflectance is 1. And this is not useful for many applications. We want to have transparent metals. We want to have something which is metallic, but with a reflectance only being to 1, fully reflective at low energy, not at the visible. We want to have something like that, fully reflecting at low energy, but transparent at the visible. This parameter here, the crucial parameter here, is the plasma frequency. The plasma frequency is written here, is depending on how many electrons do you have and the effective mass. Obviously, in a normal metal, N is very large, the effective mass is very small, and the plasma frequency is very high. We want to have something with a big number of electrons and transparent of the visible, so we need a large effective mass here to push the plasma frequency down. This is what we want to have, and why we want transparent metals. And there are many, many applications of transparent metals, and I'm going to show just some of them. in all laptops, all the iPads, iPhones, whatever, in any smart telephone, all the screen is covered by a transparent metal. And the cost of the transparent metal, the screen, is basically 50% of the device. All the iPads, all the iPhones, the major part of the component, the highest price component is the screen. But not only in these electronic devices, but also smart windows are made out of transparent metals. Some less known applications are the cockpits in the planes. This is why the pilot is able to see outside without wondering about the frost in the window, or even we see the products inside the fridge in the supermarkets. So the windows do not get frost, and this is the reason why. And here is a very important application of transparent metals in photovoltaics. In photovoltaics, you have a silicon cell or whatever, but you need the light to go through, and you need to pick up electrons, so you need a transparent electrode. So in all photovoltaic cells, you have a transparent electrode at the top. And this is a very important application, demanding a huge amount of transparent metals. So far, the most common transparent metal is indium tin oxide, and I would like just to make a comment about indium. This is a plot taken from Germany, from the Netherlands, a study done by the Netherlands Ministry of Industry, I think it was, or Economy, I'm not sure. And this is the consumption of indium at this moment only for photovoltaics, and this is the consumption expected for 2030. This is the production, the mondial production of indium nowadays. So the consumption that they schedule in 10 years' time is well above what is being produced now. So obviously there is a problem here, no? So there is a problem with the production of indium, but not only that. Indium is here in the periodic table. This is a very interesting periodic table where the size and the colors of the elements are related to their abundance and their risk. Indium is here in red and very small. So that means that there is a little amount of indium in the planet and is a very risky material to obtain. So indium is really a problem, but everything relies on indium. So it's obvious that we do need to find a different alternative to indium. And this is what we are trying to do in this direction. We need something, a material which is well-conducting, transmit optical transparent at the visible, and of course the plasma frequency at the infrared if possible. So we need a material with a large number of carriers to get the largest conductivity, as small as possible effective mass to get a large conductivity, but at the same time keeping this number of plasma frequency at the infrared. The standard material, as I mentioned, is indium tin oxide, which is an indium oxide doped with tin. So it's an indium oxide. Indium oxide is a transparent metal between a big gap between the oxygen band and the indium empty 5s bands, and then doped with tin. You get some donor defects here and some electrons in the conduction band. So you get something with a large gap here and some electrons here. This is going to be potentially a transparent metal. In fact, it turns out that indium can be doped to get a metallic, indium oxide can be doped to get a metallic behavior and still being transparent. The idea that we are trying at this moment to pursue is to go to a different strategy, is to take a metal in which we do have a gap, and the electrons here have a heavy mass. If the electrons here have a heavy mass, this number is going to be very large, and even if n is very large, 10 to 23 is not a doped material, it's an intrinsic material, the plasma frequency can be very small, well, very small, down to the infrared. And this idea of trying to use materials with a heavy mass of the electrons in the conduction band is an idea that is somehow defined by the word correlated transparent metals, assuming that the correlation is the responsible for the heavy mass of the electrons. What candidate materials for these applications, strontium vanadate is a metal, strontium novate is a metal, strontium molybdate is a metal, and so on. So let's see if it works. Obviously, one needs this property, And it turns out experimentally that strontium vanadate is at the visible. It's transparent at the visible, so the effective mass is large enough. Why strontium vanadate is a metal? First, it's a perovskite. We would have this electronic configuration, strontium 2+, vanadium 4+, and that means that you have one electron in the d band. So this material has one electron in a T2G band, so 1,6 full, so it's going to be a metal. And the same happens with the strontium niobate. Sorry. And this is a plot that taken from this paper published in Nature a couple of years ago. This is the conductivity versus the plasma frequency for a number of materials. And you see here is the semiconductors, here is some metals. The metals, as I mentioned before, the plasma frequencies at high energy are not useful for that. Those are the semiconductors I mentioned, indium tin oxide, for instance, and the vanadate, strontium vanadate and calcium vanadate are at the middle. So they are transparent at the visible, they have a good conductivity, so in principle they are good candidates. And here's what I summarize here. And it was proposed that the properties of these materials, these wonderful properties being conducting and transparent at the visible, the plasma frequency at the infrared, is related to the correlated nature of the electrons in the system. So this is the question. This is correct? All the data really support this view or not? Huh? So let's go. Let's see what we can learn about. So I'm going to talk about that. This issue is really the correlated nature of the carriers responsible for the effective mass, the large effective mass, or not. I'm going to comment a bit on how the films are grown. Then we're going to discuss the possible origin of this large mass, and later on, if I do have time, I'm going to comment on the optical response, in particular how to excite plasmons in this system. So films, the strontium vanadate films, and this is also true for strontium niobium, require a very harsh condition, or extremely reducting conditions, and are very challenged to get films of high conductivity. Films in Barcelona were grown by PLD, and this plot indicates that you need high temperature and very low pressure to get the optimal materials, otherwise you get a mixture of phases and blah, blah, blah. So you need this high temperature and low pressure, and in terms of PLD growth, this is critical, because when you go to low pressure, then the energy of the plasma is very high. That means that you are creating a lot of point defects in the film, and the residual resistivity of your film is going to be larger. So you need a low pressure, but at the same time, you need to reduce the number of point defects in the film. And we overcome this difficulty using an auxiliary argon gas in the chamber at the lowest pressure. We put a bit of argon, and then you reduce the energy of the plasma, you increase the residual resistivity, and you can get the optimal films. And in that way, using this trick, using a plasma, argon gas, filling the chamber before starting the deposition, we managed to reduce the point defects and to increase the residual resistance. And you see that this is the value of resistance at the lowest temperature grown in film. This is the room temperature, is the low temperature. And you see that this number is much more than previously reported. The resistivity ratio in our films about between 10 and 20, which is far away from these points obtained by MBE, but definitely better than before. So we do have now a way to obtain films at room temperature with standard conductivity of strontium vanadate, which is almost the same than platinum, and with a low temperature resistivity comparable, I would say, to the MBE. So we do have now, we do have the films, those are transparent. This is the film from MBE, and that is depending on the grow conditions, we can get more or less transparency. And these are examples of the films. Now an important point, what about the plasma frequency? That was the first hallmark. Well, here is the real part of the permittivity versus the energy for different films grown on different substrates and different temperatures, and you see that they cross zero somewhere here. And this is a fingerprint of the plasma frequency. Here you have a zoom of this crossing point, and better you see this plot. Here is this energy taken here as a function of the number of electrons measured by Hall effect on samples grown on different films on different substrates. And this plot shows that the plasma frequency depends on the substrate you have used, lanthanum LSAT or LAO or STO. But more important than that, it shows that for a given concentration, the plasma frequency is different. See, depending, for a given concentration, let's say 2.0 10 to 22, in films going on STO, we will have one plasma frequency, and on NGO and LAO, we have another plasma frequency. So the number of electrons is not enough to determine the plasma frequency. Something else plays a role. It's not only the number of electrons who determine the effective mass of the carriers. That's it. So the question is, the fact that the plasma frequency varies, even if the carrier concentration is the same, that means that the effective mass is not the same. So that is questions if really the correlations among the electrons, which should be dictated by the number of electrons, is the same or is the responsible for the enhance of the effective mass or not. And that is what I'm going to address this point. Here it's clear that the plasma frequency varies even if the carrier concentration is the same. So that suggests that electron-electron correlations may not be the only responsible, something else may play a role. So let's go now to the point of electron-electron correlations. And the easiest way to identify the role of correlations in a metal is to measure the resistivity. You know the resistivity in a normal metal is typically linear with temperature, and that is related to the excitation or the scattering with phonons in the system. If you have now in this metal, you have a huge number of electrons with a lot of scattering among them, then you don't have this term, Bt, but you have a term which is T squared. This T squared is proportionally related to the scattering among electrons. This is typical of correlated metals. So let's see, we have copied right now the presentation from my computer to this computer, and some symbols has gone away. So I have not checked before, so I'm sorry for that. So this is the resistivity, this is the resistivity, this is the resistivity I mentioned, and that should be the mobility that goes with T squared. So the resistivity goes with T squared as a function or due to scattering electron-electron, and that should be very important if the system is strongly correlated. Well, let's see the data. This is the resistivity versus temperature of a films of a given thickness on a different substrates. This is the plot of the resistance on a given substrate as a function of pressure, and this is the plot, the resistivity of the films as a function of temperature on a given substrate and a given pressure as a function of thickness. You see that in all cases you have a kind of curvature here, suggesting that maybe a T squared dependence could explain the data, and that is what a plot of resistivity versus T squared shows. It's more or less linear, but obviously it's not perfect the fit, but this is the standard result, and those are the fingerprints that people take, or the data that the people take are fingerprints of the electron-electron scattering in metals. So let's see what we can learn from that. So here is the plot of the slope, taken from here, the slope of this straight line, almost straight lines, as a function of n, number of carriers measured by Hall effect. And you see that the slope changes by order of magnitude, varying n. And this is also seen in this plot where we have collected data taken from other autos and related materials, not vanadates, other dope insulators in which you have few electrons in the conduction band. For instance, dope strontium titanate. In all cases, you see that the amplitude of the T squared term varies enormously with the number of carriers. Not only that, the slope is almost 1 over n. This is 1 over length. This is the resistivity of a metal. It should be proportional to the, inversely proportional to the n. So that's true. This is the amplitude of resistance. Is inversely proportional to n. That's good. But should be depending on the scattering. And that shows that the scattering, this data shows the scattering term does not depend on n, which is at odds, which you would expect for a correlated metal. The more electrons you put, the higher should be the scattering. This is not the case. Data doesn't show that. So here is a problem. Without going into the details, it's obvious that there is a problem here. There is also a numerical problem. This amplitude of the T squared term is, you can find in the books of Mott and Ashcroft or whatever. You're going to see that you can evaluate in that way. So you do the evaluation. You know almost all parameters. You know all parameters. And you get the amplitude is 10 to minus 11. And here, you are far from that. So there is a problem on the physical dependence on n. There is a problem on the magnitude of A. And there is another problem. already I mentioned, the quality of the T-square fit is not good. So really, this plot was not a straight line. And this is better seen here. This is the data, and here is the quality of the T-square loop, the fit. Obviously, the fit was not good enough. So neither the fit, neither the physical dependence of the prefactor of the T-square, neither the value of the amplitude are good enough. So there is a clear problem here, and the discrepancy between the raw data or the experimental data and the fit becomes more obvious as the quality of the film increases. When the residual resistivity is larger, the discrepancy is larger. So this plot or this idea is not convincing. There is another issue. In a normal metal, you take a metal with one electron in the conduction band. That is going to be, in the simplest case of a Sommerfeld material, even if you put correlations in there, the Fermi surface is going to be a sphere. And if in a cubic material like this one, if the Fermi surface is going to be a sphere, the magnetic resistance should be 0. But there is a clear magnetic resistance. A standard magnetic resistance, I would say, almost the B square dependence. This is a standard magnetic resistance of a material where carriers have a multi-band character. More than one band participate in the conduction band. So the picture of one single band describing the properties does not hold, and the picture of strongly correlated metals does not explain the data. We measure the effective mass of the carriers, not only from the plasma frequency, but also using Seebeck effect. Here you see the data from Seebeck effect. This is the Seebeck effect as a function of temperature, a beautiful straight line as expected for a metal. From the slope you determine the mass, and it's roughly 5. So this is a really heavy electrons. So data fits with the idea that the electrons are heavy, but data do not fit with the idea of a strongly correlated electrons in the metal. And that is what I have summarized here. I'm not going to repeat. So now the question is how to go beyond that. Can we do better? Can we describe these properties in a different framework which may be more successful? And for that, I'm going to explore the Polarization nature of the lattice. And finally, time permitting, I'm going to comment on the magnetic resistance and the quasi-two-dimensional characteristics of the Fermi surface in these materials. First, in oxides, and in particular in perovskites, there are many fingerprints that electron-phonon coupling could be very important. Not in those metals, but in other materials, some people did in the past some experiments. And here I'm plotting some data, PRL 2008. This is the plasma frequency obtained from an strontium titanate, in which they have measured the plasma frequency as a function of the carrier density. And it's obvious that the data should go along these open points here, but in fact they go here. So the mass is larger than that would be expected if the electrons would be almost free. So the mass is depending on how many electrons do you have. So that shows that there is some indication of electron-phonon coupling. And another and more beautiful experiment, this is just recently appeared in Science Report, is the critical temperature of n-doped strontium titanate. The critical temperature n-doped strontium titanate is superconducting at low temperature. You change the isotope from oxygen 16 to oxygen 18, and the critical temperature changes. Obviously, the electrons are coupled to the lattice, no doubt. There are also spectroscopic evidence of electron-phonon coupling in oxides. This is a very old paper in superconducting materials in the cuprates, and the departure that you see, this is ARPES, and you see this departure that you see here from this strange linear behavior is taken as a fingerprint of the presence of some bosons, but in the cuprates you have excitations which are magnetic, so maybe the excitations come from the magnetic aspect of the material. So nobody knows so far which is the physical origin of this discrepancy, but in vanadate you have this kink here, is also taken as a fingerprint of the electrons coupled to some bosons. Vanadates are not magnetic, so maybe here is just a fingerprint of the coupling to the lattice. So there are some indications, so let's explore that way. And here is the resistivity in the simplest possible way described in a Polarization system, in which you have the coupling to the electron-phonon coupling is related to this term, 1/tau, is described here, in which I'm taking the simplest approximation in which the carriers are only coupled to one particular phonon, omega 0, whatever it is. And now let's see if this data can be described in that way. So it's very easy. Now you can fit the data using this expression, and we can extract this parameter and omega 0 from the fit. And that is what you get. This is the red points are the all fitting that I showed you before, T-square standard electron-electron correlation plot. And now you see the dot points on top of the experimental data, the green points, and you cannot not even distinguish in this scale. So the fit is just perfect. And again, the quality of the fit is better when the films are the highest quality. So it's obvious that the fit works and works better. The fit is nothing, just a fit, so I cannot take as a religion, but the fit is better, no doubt. And it's clear that changing the film on different substrates of 10 nanometer, but on different substrates, the fit works. And now I can take this plot or this fit as a fingerprint of the omega 0 on the corresponding film, which is grown on a different substrate. So the substrates maybe impose a different strain or whatever. Maybe the phonons is different. So I'm going to, this is the phonon frequency as a function of the distortion of the lattice parameter measured by X-ray. And you see that all the data fall approximately in this line. And here there are data from films made in Barcelona and also films taken from the literature, these points here. And the films that I was describing before, the same things on different films as this green, this blue, and this red. Those are the omega 0. So it seems that indeed omega 0, the frequency of the phonon, which is coupled apparently to the electrons, can be controlled by C/8, the distortion of the lattice. One can also determine the electron phonon parameter, which is the prefactor, and this is the prefactor as extracted from the fit, and here transformed into a more convenient unit is plotted here, but it's the same parameter. And from that, one can determine the effective mass of the carriers and the electron phonon parameter, coupling parameter. And that is what you get. This is the electron phonon coupling parameter in these oxides, which is about 7, which is something similar that was extracted from the spectroscopic data that I showed you before. The effective mass is going to be very large, associated to this electron phonon coupling, and from this plot you extract an effective mass between 6 and 7, depending on C/A, which is quite comparable to the civic data. Final comment, I mentioned that in these vanadates, we have one electron in a degenerate T2G band where six states are available. It's obviously metal. If that would be a spherical Fermi surface, I would not get any magnetoresistance, but magnetoresistance is there. So I cannot escape from the data. But if I pay a bit of attention to the electronic structure of strontium vanadate, it's obvious that the Fermi surface is not a sphere. In fact, it's the intersection of three different cylinders, because there is only mixing of orbitals in 2 directions, not in 3. There is always one direction in which one orbital is never mixed. So you have one cylinder, one direction, one cylinder in the other, one cylinder in the other. So the Fermi surface is not a sphere first, and you see that there are 3 bands crossing. So it's obvious that the magnetoresistance should come. This contribution should always give a magnetoresistance, which is we do observe. So with that, I think that I have made the, let's say, first statement showing that one can go beyond the electron-electron picture and saying that electron phonon coupling can be important. What I have shown is that phonons appear to be modified by the lattice distortion, means C/A, in the same way that resistivity is modified. I have not demonstrated a direct coupling between carrier transport properties and omega. I have shown that both of them are in the very same way, but I cannot yet establish a causality ratio. That will come in the future. I'm going to now address the last point. I have mentioned the plasma frequency a couple of times or several times. Plasma frequency, if you go to the textbook of Kittel, say plasma frequency is when the omega real part of permittivity crosses 0. That's fine. But what happens at this frequency? Epsilon 1 goes to 0, but what happens? Where which is the response of my electronic system. And then you go to the Kittle's book, and next to a couple of pages later, and he speaks about plasmon excitations. And then the question is that at the plasma frequency, have we excited a plasmon or not? Or just a crossing point which physical origin I don't know what it is. And then you check the book and say, well, a plasma excitation is a collective motion of electrons. So the electronic system starts to breathe, no, somehow? And then you ask yourself, have I excited with a light a plasmon? And then Kittle's book puts you a question, at least to me. Plasmon in the Kittle's book, plasmon is a longitudinal excitation. But light is a transverse excitation. How can I excite something that goes like that with a transverse excitation? And then I start having problems myself. But thanks to the coronavirus, I had some time to read about it. Being home, yes. And I read a couple of papers dealing with a plasmonic response of vanadates or related materials, strontium niobate. This paper was published April 2017 and say, they show some absorption of light at the plasma frequency and say, maybe this is a surface plasmon. You know that plasmons can be surface or can be bulk. Okay? They say, maybe surface plasmon. Maybe. Then that was April. But in May, they say, well, this is unlike to be conventional surface plasmon. Because surface plasmon, they continue, cannot be excited by light. It's the same group, just 1 month different, basically. So it's obvious that the situation was not so clear, at least to me, and probably for them neither. So I thought, we need to think about it. First, obviously, we determined the plasmon resonance for all the films, measuring the ellipsometry, and we determined the transparency, we did everything. So that was clear that we had the crossing epsilon 1 equal to 0. At the plasma frequency, that was the edge of transmittance, so that was good. Or the reflectance, that was good. Here you have an example. It's a film on LSAT, one of the substrates, right? And you see here epsilon 1 crossing 0, and this is the plasma. The plasmon position, the position of the plasma energy at this point. And you see that at this point you don't have any bulk absorption. You don't see here absorption and transition in the bulk. Eh? So you excite the plasmon here. And here is for a real part and here, sorry. No, this is a strontium niobium film and this is a strontium vanadate films. This one is a strontium vanadate, this is a strontium niobium. The number of electrons is the same, but in niobium the bandwidth is larger, the mass is smaller, and then the frequency goes to higher frequency as shown in this sketch. So that is all. Here is the absorption peak. This is the imaginary part, the absorption, the part of the optical absorption at this frequency. It's clear that there is absorption peak. Which is the physical origin of this absorption? This is why I put here, who absorbs the energy, no? Are plasmon excited by light? And that brings me back to the question of the Kittle's book I was joking before. And the idea at the end of the day was pretty clear, and thanks again to the virus. I had time to go back to all books by Félix Abelès, a French optics, well, somebody working in optics in France. Sorry, I don't know how to say that. And these people already noticed something very simple that apparently somebody else had forgotten. If you have a film, whatever it is, metallic film, and here I have depicted a possible excitation, a possible plasmon, transverse plasmon moving in this direction, right? Light is coming here at some angle, tilted angle, obliquous angle. Now this light is polarized P, so it's in the plane of the screen. The polarization field is in the plane of the screen. It's going to have a vertical component and a horizontal component. The horizontal component is not going to excite anything here because the film is infinite. But the vertical component is going to excite this motion. So obliquous light, P-type, P polarized, not S. P is going to be able to polarize. And that is what it happens. We measure the reflectance and the transmittance for S and for P. And indeed for P, you see a sharp dip in transmission because you excite the P component of the light or the vertical component of the p-polarized light excites the plasmon. So you can excite plasmons with light in these films, and now you can imagine to do plasmonic at infrared, not plasmonic at the visible, plasmonic at infrared using these materials, and for many applications that could be very useful. Summarizing, I start from the idea of electron-correlated matter or electron-correlated electronic systems in these materials. I end up with a situation in which the best description or better description is given in terms of electron phonon coupling and anisotropy of the Fermi surface and the multi-character subsidial. And the resulting multi-character of the conducting electrons is responsible for the magnetoresistance. And I show you that you can, in these optically transparent films, you can induce plasmonic resonance and do with them infrared plasmonics, which is not possible obviously with a normal metal, and then offering new opportunities for optics and technology. I should not finish without thanking Mathieu Mirjolet. He did the PhD in on vanadates, and he's the responsible for all the results I have presented. So all the merit is his merit, but we also collaborate with a number of people. José Valentí in Germany doing DFT calculations and demonstrating that indeed there is electron phonon coupling that so far was not identifying these materials, infrared spectroscopy to measure the plasmonic response in a couple of different laboratories, measuring the Seebeck coefficient, transmittance measurements, and some support for the growth of strontium niobate that I have not described in detail. Thank you for your attention.
Okay, thank you very much for your inspiring talk. So we have time for a very, very short question. Please, Marius.
Thank you for the presentation. You mentioned that a possible source for the mass enhancement, which you claim to be critical, to be the electron phonon coupling. However, looking at the Fermi surface, the electronic structure, we see those cylindrical shapes. That means in one direction, the effective mass is practically infinite, and the band structure shows that it's actually a flat band.
Is this one, the flat one is the effective mass infinite. Exactly.
Right, so only the flat band is not necessarily, you actually have infinite band structure, infinite effective mass. Do you really need electron phonon coupling? Moreover,
those electrons who do have infinite mass are not going to contribute to the transport, so I forget. The ones that have a finite mass, they are going to contribute. And those ones, if I take only the electronic structure, this effective mass, what I'm claiming is that it's not enough to describe the electron properties. I'm not able to describe the T-square dependence.
Right.
That's the point.
Right.
The point.
And another short question. You mentioned that the electron phonon coupling strength increases with the phonon frequency. This, do you have an explanation for that? I mean, normally the electron phonon coupling strength should not depend on the energy of the phonon, or not necessarily.
No. I understand the question. Here referring to a plot I show in which the omega 0 varies with C over T. We don't know yet why the omega 0 and the electron phonon coupling varies with C over T. What we have already verified we have already predicted, or some of the colleagues have calculated, is how the phonon modes vary with the strain. That is clear and go in the direction we have seen. We don't have yet the output of why the electron phonon coupling increases or decreases. So no answer for that.
Okay, thank you.
This calculation is on the way. No answer for that.
Thank you very much, and I think we can discuss later during the breaks and during the evening. So I invite now Valérie Demange present us the talk Oxide Nanosheets at Seed Layers for Epitaxial Growth of Complex Oxides. Please, Valérie.
So in the meantime, thank you. So first of all, I would like to thank the organizers to give me the opportunity to present this work in front of you today. I told this with oxide nanosheets as seed layer for the growth of complex oxides and also for the growth of platinum. This is a collaborative work between 5 laboratories in France. My laboratory is the Institute of Chemistry Science in Rennes, and we have worked on this subject with the CRISMAT in Caen, the P' in Poitiers, the GEMAC in Versailles, and the Institute of Physics in Rennes. Well, okay. You know, all of you know very well that to obtain high properties for functional oxide as a thin films, it is necessary to go it as with an epitaxy, which is obtained with a single crystalline oxide substrate, like, for example, strontium titanate. And this is due to the fact that there is a small differences between the crystal structure of the substrate and the film, and also a small mismatch, as for instance with these schemes. These complex oxide substrates have good properties, but they are expensive, they are difficult to process, and also they have a limited size, and altogether it is a limitation for the integration in device. So it's very sensitive, this button. So for a long time now, we would like to integrate these oxides on a more interesting substrate as silicon and glass, which are more adapted for industrial applications. And we have some functionality of perovskite oxides, for example, in silicon-based in microelectronics, but also, as we have seen just before, we have also some oxides which are interesting because they are transparent conductor outside, and in this case, this is the glass, the main important substrate. But of course, there is no epitaxy of oxide on silicon and glass because of differences, structural and also chemical. There is also a problem with the large thermal mismatch between substrate and thin films. And at the end, the silicon also reacts very highly with oxygen to form the amorphous silica on the top. So the films we grow on it are present very low crystalline quality, and of course you have a degradation of properties in this case. So integrating oxides on silicon and glass, it's still a great challenge for industrial application. So some attempts were made in the past last year to grow oxide on silicon, and the first breakthrough was made by Mike Key et al. In 1998. They have shown that it was possible to grow a very thin layer of strontium titanate on silicon by means of molecular beam epitaxy. And since then, a lot of other groups have presented other kind of template layer, which are listed here. But the limitations of molecular beam epitaxy are the following ones. This technique is expensive. This is a very complicated technique, as you can see on this picture. This is also a slow process with a lot of steps. And of course, there is a little use of this technique in industry. But finally, the properties of the film are not optimal yet. Some other groups have worked with other techniques, like for instance, pulse laser deposition and atomic layer depositions, with some more or less same limitations. The optimal properties are not yet reached. This is still under vacuum growth, so this is still expensive. And also, it requires high temperature of growth, which is a limitation for the use of oxide in microelectronics. Here, I will present to you today another way, which is slightly different, since in this case, we are transferring nanosheets directly on the substrate. It could be any substrate, and this is not a growth of a template layer. This is an exfoliation of a layered metal oxide, which is a parent compound, and all this process can be done at room temperature. So it was found, it was shown for the first time in 2007-2008, by 2 groups in Japan, and they have shown that it was possible to obtain a preferential orientation of different oxides. We have the list here, on nanosheets coated glass. Then in 2013, it was also shown that other kind of oxide can be also obtained on nanosheets, on platinum, or on silicon. Here I present the result of a publication from last year, actually. In this article, different groups have worked together to compare all these metals I have shown to you. So they have deposited a super-lattice of manganite on plus strontium titanate on silicon using single-layer buffer of strontium titanate by molecular beam epitaxy, also by laser beam deposition, other template layer, and so on. And they have compared also with strontium titanate thin template seed coat on two-dimensional nanosheets plus a reference sample. And here are the results. They have shown that if we compare the films, the super-lattice films deposited on nanosheets with the reference, this is the best results in terms of all properties. I mean crystalline properties and also magnetic properties. And this is due to the small lattice mismatch between these nanosheets and the strontium titanate, and also to a less clamping from the silicon substrate. So there exist a lot of oxide metal nanosheets. We have most of them are listed here. And today I will talk about mostly this one. This is a calcium niobate nanosheet. You can see here the structure in plain view. And it has a perovskite-like structure, as you can see, with a square lattice, which is close to 4, as for perovskite. And also, this kind of nanosheets have high thermal stability until 80 degrees, 100 degrees. So this is the outline of my talk. I will first, after this introduction, I will show you how to synthesize this metal oxide nanosheet and how to transfer it on glass and silicon. Then I will show you the integration of two kinds of oxides on glass, so manganate films and strontium and calcium vanadate films. And in the last part, I will show you also how we can integrate platinum on silicon thanks to the nanosheets before conclusion and perspective. So we start with the synthesis of the nanosheets. So to obtain these nanosheets, first we start with a parent compound, which is a layer perovskite Dion-Jacobson phase, with this chemical formula we have here. So in these compounds, we have potassium, calcium, niobium, and the structure you can see here is made of sheets here, which are constituted by 3 layers of octahedron, which are which sharing their corners, as like in a perovskite. The thickness of the sheet is about 1.5 nanometers. And in between each sheet, we have a layer here of potassiums. So after the exfoliation of these parent compounds, we get the nanosheets. And if we look at the in plain view, we have this perovskite-like structure. So how to get first the parent compound? We use a conventional solid-state reaction at high temperature. We mixed together the precursor with an excess of the potassium carbonate because of the volatility of the potassium. We obtain this white powder, and by scanning electron microscopy, we can see that we have plates for the crystals of this powder, and then we check the crystallinity of the powder by the conventional structural and microstructural technique. Then we have to exfoliate this material. This is a two-step problem. Two-step method process by it's a chemical process. The first step is to put the powder in nitric acid and at room temperature with stirring. It takes 3 days to exchange here the potassium ions by protons from the acid. And you obtain another layer compound. And again, we can check the materials. And for instance, by the composition, by measuring by energy dispersive spectroscopy, we can see that we have lost almost all the potassium in this material. Also, we can check the process by X-ray diffraction, and in particular, the parent compound have a strong peak related to the basal plane, and these peaks are shifted because the interlayer has changed. So this is a way for us to control that the process is running well. So the second step of the exfoliation, this is the real exfoliation, is to put this powder now in other liquid containing water, and tetrabutyl-ammonium hydroxide. And we have here a reaction between the OH- ion of this ammonium hydroxide with the protons of the materials. and both forms water, and then the crystal falls apart to form nanosheets, which are negatively charged, and they react with the TRBA plus we have here to form this colloidal solution. So at the end, we have a colloidal solution of the nanosheets in this bottle. So to check if it works, we can send a laser on the solution. We have this so-called Tyndall effect, which corresponds to a diffusion of the light in the solution. But it's not enough, because if we look now to the particles inside by transmission electron microscopy, we see here that we have completely failed, and it's necessary to check the solution with by this technique, for instance. Here we have succeed with, you can see here nicely the nanosheets with the shape, the thickness, and also we can check the crystallinity by electron diffraction. So we see here we have the square we were expected for cubic materials, and also we have seen that you have actually some weak super reflections corresponding to octahedral tilting in the perovskite layer. And again, we can check the composition, and here we have disappearance of the potassium in the nanosheets. So next, to transfer the nanosheet to a substrate, we can use two methods. The first one is the so-called long-mirror budget method. This is a very old method to deposit organic particles. Yet it is used for the deposition of nanosheets. So the principle is here, we put in this container the liquid, the colloidal solutions. Here we have a hole, which is a dipping well for the substrate, which is here. So we can dip the substrate in here. And then we have these two barriers, which are moving together to go in this direction and to push the nanosheets, which are at the interface between the liquid and the air, to transfer the material on the substrate. So we measure the surface pressure of the liquid here as a function of the compression percentage of the surface. And at some points, we decide to fix the surface pressure here, just before this plateau. And this plateau corresponds to a very high covering here at the liquid air interface. And then we move up the substrate, and the barrier manage to still have this value here. So therefore, they are pushing the nanosheets layer on the substrate. The second method is quite recent. It was published last year, actually, by the group of Professor Sasaki in Japan. And they have shown that it was easier to put a droplet of the solution here on the substrate, which is on a hot plate at around 100 degrees. And they have shown that we have some different process inside a mahogany convention, which is a mass transfer along an interface due to a gradient of the surface tension of the liquid. And here this is caused by the temperature gradient. Also, this is a combination with attractive capillarity forces between nanosheets. And the second step here is to remove the liquid with a pipette. And what happens is that some nanosheets are going vertically and are trapped at the interface between the liquid and the air. And finally, we have a shrinkage of the droplet. So here, this film is deposited on the substrate. And finally, when the liquid is entirely removed, we have an uniform deposition of nanosheets on the substrate. This method is really interesting because it's very fast. It's very economical because we don't have to use so much solution, so we don't waste materials. Also, we can manage more easily the deposition on different kind of substrates, which are hydrophobic or hydrophilic. It's more easy than with the long-mirror budget method. And we can also use very large substrates. The main disadvantages is that we have some mark of the pipette in some location on the substrate, as you can see here. We have this kind of coffee rings, and also it is very operator depending. But finally, we have succeeded to deposit the nanosheets by both technique, long-mirror budget or dop casting on silica and on silicon and in silica. And as you can see, we have a very high recovering of the substrate by the nanosheets. Some of them are, at some place we have two kinds of nanosheets up together. We can clean this by a careful rubbing with a Q-tip. So the nanosheets are edge to edge, but they are no adhering in plane. So it means that when we will go film oxide on top of it, we will get a texturation of the film. We can also characterize the nanosheets after the deposition. So by out-of-plane X-ray diffraction, you have nothing really relevant, of course. But by in-plane X-ray diffraction with a laboratory diffractometer, we can have nice peaks, and it confirms the crystalline character of the nanosheets. So now I will show you the result of the integration of oxide films on glass. So first with this manganite. The work was done by Alexis Boileau in CRISMAT. So he has deposited by pulse laser deposition this magnetic oxide on glass directly, and he has obtained something which is crystalline at least, but polycrystalline, as you can see. And when we have deposited the same material on the nanosheets covering glass, we have only one orientation, which is the one, which is the one we expected. Also, you have shown that the weight of the working curve is less important on glass, on nanosheets than on glass, and that the scattering domains are also larger. This result was confirmed by electron backscattering diffraction, and you can see here the texturation, the strong texturation with this out-of-plane map, when in plane we don't have any ordering actually. By AFM, we can see that the films present a granular morphology when they are directly deposited on glass. And here we can see also below the form of the nanosheet, which are preserved unless the temperature. The colleagues in Caen have also performed magnetic properties, and they have compared the film directly grown on glass here in blue, grown on nanosheets in red, and grown directly on a single crystalline strontium titanate as a reference in black. So we can see that concerning the magnetization as a function of the temperature, that manganite on nanosheets present a behavior which is very close to the one on the strontium titanate substrate, compared to the film made directly on glass. So also, if we look at the magnetization as a version of the field, as a function of the field, we can see also that the materials grown on nanosheets present are close to the one made on the reference substrate. So above results are due to the fact that you have larger magnetic domains and also a preferential orientation. Now, if we look at the resistivity as a function of the temperature under a field or without a field, we see here the reference on single crystalline substrate, and here the material on glass, and in the middle we have something intermediate for the material on nanosheets. And this is due actually to the fact that you have no ordering in plane, so we have a lot of grain boundaries in the materials. And finally, concerning the magnetoresistance as a function of the temperature, at this time we see that material directly deposited on glass and on nanosheet are very close to each other, and you have then a very strong magnetoresistance response, again thanks to the grain boundaries we have in the films. I will now move to the second oxide we have deposited. It's vanadates, strontium vanadates and calcium vanadates films. So all this part was already presented by Professor Franco-Berta just now. This material, we need transparent conductors for important technological application as electrodes, and these electrons require high electrical conductivity and high optical transparency. So we have seen already that for metals there are some antagonism between the two necessary properties, and in particular, so we have to try to optimize this N on M star ratio. Also, we have already seen that Indium Tin Oxide is a very excellent transparent conducting material. So since the indium is very rare, we are looking for other materials, as for instance, this correlated strontium vanadate and calcium vanadate. So here the colleagues in Caen have grown both materials by pulse laser deposition, and they have obtained this result. They can show that above 400 degrees, the material is crystalline and present very good conductive property, and also they are transparent, and this is what we wanted. But below this temperature, actually the material is amorphous and it is insulating. And also to integrate this kind of material on glass, like this one, which is Corning Ingle XG slim glass. This is the glass we can find in a smartphone, for instance, on a television. We need to integrate this material, and if we grow this kind of oxides on glass at 400 degrees, it's amorphous, but even at higher temperature, at 700 degrees, it also amorphous. So this is really a problem, because since this is amorphous, this is insulating. So we try to use, this is a motivation to use nanosheets to induce a crystalline growth of these materials. Nanosheets present low misfits with both vanadats, and also they are fully transparent in the visible. So the stack is the following one. You have a glass substrate, you have a nanosheet here, then you have the films made by PLD, and then you have an amorphous capping layer to protect the vanadat films. So here, as a result, as you can see, all the films grown at different temperature are transparent. And more important, they are crystalline. And we can see that you have a very strong orientation along the 001 direction for both materials, in particular at this temperature, 500 degrees Celsius. And again, we can confirm the strong texturation by electron back scattering diffraction. Also, we have checked the composition of the films. Since we are on glass, we can have some diffusion of the element of the glass in the film, and actually this is what happens. We see here, this is energy dispersive spectroscopy analysis, the presence of silicon and also the presence of niobium in the spectra, indicating that you have a diffusion of elements in the films. So the transfer measurements were made, and also optical properties by ellipsometry. And with these two techniques, it was possible to extract different parameters. The resistivity first, as you can see, this is very low, until 600 degrees Celsius. Then the carrier mobility was measured, that it is really high, also higher than for indium tin oxide. The carrier mobility is present like a parabolic curve, indicating that the maximum is around 550 degrees for these materials. And finally, the mass, the effective mass, are also extracted, and they are close to the value of the bulk value. By ellipsometry, it was also the plasma frequency was also measured, and you can see that is below the visible range. This is what you wanted to have, because the threshold is about 1.6 electron volt. And finally, the optical property by transmission. The transmittance was also measured, and as you can see, this is fully transparent and comparable to what we can have with indium tin oxide. So if we put the results in arc figure of merit, we can see that our results are close to the other transparent conductive oxide, and this is really a good result. And if we look again to this diagram, we see we are here, and it's not so bad. So I didn't talk of integration of oxide on silicon yet. We have some results, but I will now move to something else, which is integration of platinum on silicon. So as you know, platinum is an electrode material for integration of functional oxide on silicon. We can have it at bottom electron or as top electron. For the bottom electron, a preferential orientation is needed, an isotropic texturation, and also a high crystallinity are also required. The natural growth of platinum on silicon is a 1-1-1 orientation, and to obtain a very good electrode, we need to grow at higher than 600 degrees with a very small working curve width. But the problem is this is also the limitation for the integration of functional oxide in microelectronics. So Gilles Poulain in Caen had the idea to grow platinum directly on nanosheets. It was never done before. So they have gone two kinds of samples. The first one is a silicon recovered by a silica, then a thin layer of titanate, which is here to increase the adhesion of platinum on the substrate, and versus the same thing, but instead of the titanate, you have the nanosheet seed layer here below the platinum. Different temperatures, of course, have been looked at, and so we have worked with 2 atmospheres, one under pure argon and the second one which is a mixture of argon and oxygen. So here as a result for the growth under pure argon, first you can see that in both cases we have the 1-1-1 orientation, and we have a shift of the peak indicating that we have a shift of the lattice parameter, which is due to thermal stress differences between both substrate and films. And as you can see, on both samples, you have exactly the same behavior. But the most important result is here. We have already something on the nanosheets from 200 degrees Celsius versus the same result for about 600 degrees with the normal substrate. So this is a very important result for the microelectronics. And also, if we look at the right of the working curve, we have something very low for the material deposit on nanosheets. And this is also something which is really important for the microelectronics. Also, the platinum presents larger grain size while they are grown on nanosheets. And the second part of the study was to look at the platinum under argon plus oxygen. And the motivation is the following one. It was shown some years ago that if you have the orientation 200 for the platinum, we have better ferroelectric properties for a number of devices. But the problem is that to obtain this 200 orientation, we need to work at very high temperature, and also we need to work with a mixture of argon and oxygen. Some attempts were made also to obtain the film at a lower temperature, but without this adhesive layer. And then we have a poor adhesion to the substrate. So in all the cases, the temperature is very high. So here the idea was to try also with nanosheets what happens. And on the normal substrate, nothing happens special. We still have this 1-1-1 direction. But with the film on nanosheets, actually, after 500 degrees, we can see that you have the appearance of the 201 direction. Here, it's a zoom of this area. Clearly, after 550 degrees, we have a 201 orientation. And which is also really interesting is that this wide of the working curve is also very low, lower than 0.8 degrees. So here we can have an orientation control of the platinum film thanks to the nanosheets. So I will come now to the conclusion of the talk. So I have shown you that thanks to nanosheets we can go for a lot of functional oxides with properties which are in the state of the art for some of them. And we have some integration of also vanadats with excellent properties. For the growth of platinum, we have seen that it was possible to lower the growth of the materials at 200 degrees, which is a very good result. And also, that we can change the orientation of the platinum from 111 to 200 by adding oxygen in the atmosphere. So some perspective to this work. First, we would like to have larger nanosheets to increase a little bit our properties. And you have some first results by obtaining large crystals by molten sand methods. Also, we would like to go towards flexible substrate. Here I have an example of a potassium niobate film which was grown on mica. Directly on mica, we have something which is not really good, as you can see on this micrograph. But if you insert nanosheets on the mica, then you have a preferential orientation, and you have a very good microstructure aspect of the films. So mica is transparent, it is easy to delimitate, and we can transfer all the stack on something else, like polymer, for instance, or silicon again. Concerning the platinum growth of nanosheet, so the next step now will be to go an oxide on the platinum nanosheet silicon stack to see what happens, and also to try to decrease the growth temperature when we have this 200 orientation by modifying the deposition parameters. And the last perspective at the moment for us is to work with other nanosheets. So we have a library of nanosheets at home, and for the moment we are working with this one, which is a titanate. So this one has a rectangular cell, as you can see. We have succeeded to have it. We have a nice covering on silicon and silica. And the first growth of manganite was made a few weeks ago by Arnaud Fouché in Caen. And we can see that you have obtained a 011 preferential orientation of this rectangular, and this is what we wanted actually. So finally, I would like to thank the students who have worked on this subject. In Rennes, it was Florent Baudouin during his PhD, Amélia Baucher, Arnera de Brito, and in Caen, Alexis Boileau, Jacques Mangelet, and Marie Dalocchio. The work was funded by a French project, an agency. Also, most of the CM, TM, and in-plane X-ray experiments were performed on platform in Rennes. And again, I would like to thank the organizer of the workshop and thank you for your attention.
Okay. So thank you very much for this talk, and please questions. We have time for several questions. I have one question, because this platinum growth was in fact on the native silicon oxide. It was not directly on silicon, on the semiconductor.
Yes.
And do you have an idea about the thickness of the, it was 3 nanometers, or it was just the natural...
Of the platinum,
the,
you mean?
no,
the
native oxide of the silicon.
I think it was cleaned by HF first.
HF,
so I think the
yeah.
thickness should be 1 nanometer or something like that.
Yeah, okay. And did you check the crystallinity of this oxide? Is it...
No, I think it's amorphous as usual.
It's amorphous, okay. Thank you.
Just a short question. Could these nanosheets also be exfoliated mechanically, like graphene is from graphite, or something similar? Could you think about a kind of chemical treatment to allow that?
There is no publication on that at the moment for oxide. For hydroxide, actually, it's possible to have it mechanically. Someone in Strasbourg is working on that. But to answer to the question, one of my colleagues in the Institute of Physics has succeeded this summer to exfoliate mechanically a crystal I have shown to you without any chemical process, except that you have to put a polymer on this to exfoliate in the process. And this is maybe the first time it happens for this kind of oxide, actually. And of course, it will be more easier again to do that like that. But the problem now is to transfer the nanosheet itself on something else.
Okay, so it is possible.
Yes, yes, it's possible.
Yeah, other questions?
Which is the lateral size of these nanosheets? Maybe I missed the point. I mean, when you prepare the nanosheet and then you deposit the nanosheet on top of a silicon or whatever surface, which is the lateral size of these nanosheets that you are...
Most of our work was made with nanosheets sizing between 2 micrometers and 15 micrometers, something like that. And you have higher nanosheets, and for the moment we didn't have results because it fails. So in average it's 10 micrometers.
And when you grow a film on top of this layer covered with nanosheet, what happens with the grain boundaries of the nanosheets? How do they propagate into the film that you grow on top? I didn't show the results for potassium niobate films we had, but we didn't see any differences between the film grown on a reference single crystalline substrate and the other one. But the film was very thick, so I don't know. And there is also no difference for the other ones, but they are smaller grains. So. Okay, thank you.
If the nanosheets are far away from each other, can you grow like nanowires with these nanosheets as precursors, as catalyzer?
I think there is no references in the literature on that.
Okay.
I didn't see anything on that. But maybe it could be done with other nanosheets that the one I have shown for oxides, zinc oxide, for instance, things like that. That's a good question.
Are there others?
Very interesting talk. I want to ask you, how do you avoid the contamination between the ions of the nanosheets and the material that you deposit? there is any contamination, or do you control it by temperature or by other parameters?
We have seen that we have a contamination if the temperature of growth is too high. So we have a diffusion of niobium in the films. So we have to control the temperature. And otherwise, we didn't see any contamination because the nanosheets are very stable at high temperature. So it seems that it doesn't, but yes, we can degrade the nanosheets if we are working at too much high temperature.
Okay, other questions? I still have one. Do you have some adhesion test for this? Some adherence test for these layers?
Sorry, I didn't know.
The adhesion, the adhesion.
The adhesion?
Yeah.
The adhesion is made by van der Waals bonds on the substrate, and it is stable during several months, actually. But after several months, we have seen that some of the nanosheets begins to wall a little bit at the edge, and tends to go away. So
but you did not try to measure it, to do some...
No, we didn't try that.
Okay.
No.
Yeah, thank you. Okay, so thank you very much, and I invite now Brian Rodriguez to present us the talk AFM tip-induced strain effects in bismuth ferrite films, from structure phase changes to polarization switching and nanofabrication. Please.
Great, thank you very much. Thank you for the introduction, and to the organizers for the opportunity to present this work. This work was performed primarily, largely by Fengyuan Zhang. This is part of her PhD work. She graduated and defended during the pandemic. I'm going to tell a story with two parts. Both parts have to do with scanning probe microscopy, which is what our group does. And we use conducting probes to do both conducting measurements as well as PFM. But we introduced something new for our group, which is using a very stiff single crystal diamond probe to carve out nanostructures in bismuth ferrite thin films. This work was sponsored by Science Foundation Ireland and the China Scholarship Council. And we had collaborators from China, the US, and Northern Ireland. Okay, so it should be familiar to most of us here that we can use at relatively low forces PFM scanning probe technique, where you apply an AC voltage to a conducting cantilever and measure the converse piezoelectric effect, so the deformation of the film. We can do that at relatively low forces and get a nice map of the PFM amplitude and the PFM phase, where the amplitude shows how much the deformation was, and the phase is showing something about the orientation of the domains. In bismuth ferrite, if we go to a slightly higher force, we can introduce a structural phase change. So we can go from a bias-induced tetragonal phase to a mechanically induced mixed RT phase, so rhombohedral tetragonal phase. And this happens in this film at around 400 nanonewtons. And I'm basically giving away the conclusions or the end results of this work in the next two parts of this slide. But what we see when we start applying forces while we do our PFM measurements and look at switching current is basically shown here. So in this animation, we bring the tip down into contact. We can apply forces. We can calibrate the cantilever. We know exactly what force we're applying. We can measure our switching as a function of applied force. And you can see that as we go from 50 nanonewtons up to 925 nanonewtons, the coercive field is actually changing. And what happens when we measure the current during this? So initially there's no switching current that's detectable at this scale. From 50 nanonewtons on up, we start to see switching current. That switching current, in line with the change in the coercive bias, is going to lower and lower coercive biases, and the current peak is enhancing. So this is the thing that I'd like to talk about today. And then in addition, what happens if we start applying a larger force? So that's going from just purely imaging or maybe cleaning the surface a little bit to introducing a structural phase change, to enhancing switching currents and changing the coercive field, to actually modifying the surface with larger forces. So if we go to on the order of 20 micronewtons, we can do something like this and have the tip go and follow a loaded lithography pattern, or just an array like this. We can actually scratch the material and create nanostructures. So this is what I'd like to talk about today. So in terms of motivation, it's not a great motivation, but I'll tell you our motivation in terms of ferroelectric memories. And don't ask me the device that would be done with this, because I don't really know. It's a bit of a stretch. But if we think about ferroelectric memories, we have the idea of course, switching the material, and we can detect whether or not something is switched, if the domain is switched, by looking at the displacement current. So in this instance where we have a displacement current, that could be a bit of 1. Now, as we go to smaller and smaller elements, the detectable current, the current becomes smaller and smaller. So if we go to smaller and smaller elements, this is going to be very difficult to detect. So this is 10 picoamps for 300 nanometers. And if we go to even higher density, for higher density storage, we'll have smaller sizes and smaller currents. Here's another example. So in this work by Peleon Lee, you can see that we have this displacement current, the switching current, but on top of that we have an injected current that happens during the switching. And they discuss that in terms of tunneling through the dead layer, basically. So during switching, the barrier height can change. We have some interfacial layer, and as you're switching, you can get charge to be injected across, and that can lead to an enhancement orders of magnitude higher than the displacement current. And so maybe that could be used for the detection of whether or not your domain is switched in your ferroelectric memory device. On top of that, it's been reported that the dead layer can be effectively squashed with force. So you can squeeze it a little bit by applying a force with a tip. The dead layer basically isn't going to be beneficial for a ferroelectric memory device. It's going to suppress that current. So if you can make it a little bit thinner, you might be able to tunnel through that and enhance the injected current. If we look at this representation of current, of tunneling current, there's a term, the transmission coefficient, for tunneling across the interfacial layer. And if we look at this and you think about thinning that interfacial layer, that interface layer, then in principle you could enhance the current. So that's the proposal here. So can we decrease the dead layer thickness, and can that cause an increase in current, where the current is largely coming from some tunneling current through some injected charge? Okay, so the film that we're looking at is bismuth ferrite. It's about 50 nanometers thick, and it has a nice interfacial layer, a dead layer at the surface. Here we show our height image after applying a switching bias of plus and minus 8 volts. So you can see in principle that the topography has changed. Here again is our PFM amplitude and our PFM phase. As grown, the film is already in a single domain state. Here's a representative switching loop, so a nice symmetric butterfly loop, a little bit of imprint, as you can see, and a switching voltage around 4 and minus 6 or minus 7 in this case. Okay, so to illustrate the point here that the applied force can influence the switching, what we did again was start with this minus 8 and plus 8 and minus 8 switching. You can see the amplitude here. And then we started applying both a switching voltage, so in this case minus 4, which normally wasn't enough to switch the material. And we did it as a function of force. So while scanning, we start down here, we apply 100 nanonewtons. As we're scanning, we're increasing the force. And the minus 4 volts that usually didn't switch the material now switches it when we get up to 800, 900 nanonewtons. Similarly, on the other side, starting with minus 8 volts and applying a positive 2 volts, which normally wouldn't switch, we can go all the way up to 900 nanonewtons and it doesn't switch. Now, just increasing by 1 in both directions. So again, plus 8 switching, applying minus 5 along with a force, so minus 5 at 200 nanonewtons, it starts to switch. and for +3 volts, it starts to switch when we get up around 700 nanonewtons. So the influence of the force on shifting the coercive bias, I think, is clear here. Okay, and here are phase loops, or our local D33 measurements, or PFM phase loops, as a function of force. Again, maybe it's not so easy to tell, but the lighter color, yellow ones, are much wider than the higher force, dark color ones. So we've effectively shrunk, reduced the coercive field on both sides. So it's a symmetric effect in this case. And that's shown here. You can see our coercive voltage plotted as a function of loading force. And you can see that it's shrinking on both sides. The applied force is causing a reduction in the switching voltage in both cases. And from our understanding of the flexoelectric effect, we would expect that not to be symmetric. So we think that while flexoelectricity is involved, there's another thing going on in this work. Okay, so now if we look at this switching-related current, here's an IV curve showing switching, again, at the location where we were just seeing that we saw switching take place. We can map that at the same time with our PFM phase loop, and you can see that the switching takes place and the high current takes place when we have the polarization reversal. And this was recorded at 750 nanonewtons. Now, to kind of illustrate that it's just happening when we're doing switching, we do a preset pulse, and then on the first pulse back, we expect there to be switching, and then we don't expect to see currents on the subsequent pulses because we're not switching anymore. So in that case, for cycle 1, we have a nice peak, and for all the other cycles, there's no current. So we're attributing this to switching-related current. But what we don't think it is the displacement current, as I'll explain. We think it's related to like an injection or a tunneling current. Similarly, in the other direction, so in the first cycle, so preset positive, then apply a negative pulse, we only have switching current for that first event. Okay, so again, I've already shown this, but showing what happens as a function of force, we're increasing the force. You can again see both the peak magnitude increase and shift to lower switching voltages. And that's as we're increasing the force, but it's reversible. When we decrease the force, the same thing happens. And this helps rule out a little bit for us, maybe not completely, that everything that we're seeing is just because we're having better electrical contact. But that's still a concern. There's a couple of concerns that we do have. But it's symmetric in both directions, so we can plot what happens. And under the assumption that we have a 25 nanometer tip radius, and that's our contact, we can do a calculation of the polarization from these currents that we're measuring. And you can see that, while not perfectly symmetric, it is increasing with force and then decreasing with force again. And similarly, the switching voltage is decreasing and then increasing. And I think, perhaps surprisingly, it is changing the coercive voltage by a volt, which is quite large. We tried to estimate whether or not this was realistic. It's in the paper, kind of in the supplementary material. But we estimate that for that 50 nanometer film, where we have a few nanometers of dead layer, of interface layer, that this would correspond to a change in that film thickness of at least a quarter of a nanometer. And that would give rise to on the order of a volt, a little bit less than a volt. Okay, so in this part of the work, we identified polarization switching induced currents. We observed an increased loading force and that enhanced the current for both positive and negative forces. And this increased loading force decreased the switching voltage for both positive and negative. And what we think might be happening is that when we're applying this force, we're actually squeezing, we're pinching that dead layer. And in doing so, that allows for the enhancement of the tunneling current, but it also perhaps reduces the barrier a little bit. So some combination of those effects is giving rise to this enhanced current, which is orders of magnitude higher than could be possible just from switching bismuth ferrite. So I think I went over that a little too quickly. So here, I mean, this is going up to 1 to 10 to the 5 microcoulombs, and we would only expect for bismuth ferrite to have, depending on the phase, on the order of 100 microcoulombs. So it's orders of magnitudes higher, and even if we took that the area of contact was much larger, it would still be orders of magnitude higher. So we don't think it can be the displacement current itself. It has to be related to some charge injection. So we believe that this could be explained by this reduced barrier height and narrowed barrier width, kind of as shown schematically here. Okay, then the interesting thing to think about is what happens if you apply even more force? Can you get more current? What's the limit? At what point do you deform the sample? We didn't fully go down that path, but I'll show you what we did do. So we started to try to make some structures. We were kind of interested in creating functional states. We haven't quite gotten there, but we're working on it. So just to put this next part into perspective, humans have long been interested in machining, going back to these very early tools, to the earliest example of a lathe, to more modern techniques and technologies, which often make use of diamond tools. So here's an example of an AFM image of a workpiece that's been carved with a diamond cutting tool. And nowadays we do have single crystal diamond tips available with a very sharp tip radius. And so we kind of decided to try to combine the two and use a single crystal diamond tip to do machining of ferroelectrics to create nanostructures. So this comes under a number of different forms and names. So mechanical scanning probe lithography, nanomechanical machining, tip-assisted milling, and nanosculpting. And of course, it's going to depend on your tip material and properties, the normal and torsional stiffness of your tip. And it can be done in a variety of different configurations, both for imaging and tomographic modes, where you remove the material and measure what's a particular property or functionality as you're removing material. And this has been used quite widely. It was new to us when we started doing it, when we started looking into it, but a number of groups have been using AFM for lithography, for removing material. Of course, you're probably familiar with AFM for local oxidization and a bunch of other lithography approaches. And of course, for ferroelectrics, we have ferroelectric lithography. But this is removing a material in silicon, making silicon channels. Here's an example of transferring a photograph onto aluminium. Polycarbonate nanoarray. All of these are carved with an AFM tip. And this is an example of tomography. So measuring current as a function of depth. It's a destructive technique. You're removing material, but you measure the functionality each time. And the basic idea behind this is maybe there's a place for it in ferroelectric lithography. Of course, we have focus ion beam. It's very good for making small structures, but it does come at a cost with some damage that you might even repair with an AFM cleaning technique. So there might be some limitations. And so maybe in specific cases, a nanomechanical AFM-based approach might provide some usefulness. In addition, you could have self-assembled nanostructures, and in this case, deposition kind of through a stencil mass to make nanostructures. So in both cases, there might be some limitation where a nanomechanical approach with an AFM tip might be used. Other tip-assisted studies in ferroelectrics include local tip-assisted crystallization, carving holes into a material to then create a place for a polymer nanodot to be deposited. And a great example recently from Brian Huey's group in Connecticut, where they did exactly that tomographic approach, where they removed the material and measured the domain structure as a function of depth. So we started this in 2017. This was the first time it actually worked, when we used this stiff diamond tip, and this was the first structure that we got. And then we started to try to understand the process a little bit more. And perhaps we should have started with reading the literature, because a lot had already been done, but not on ferroelectric, so that it's a little bit novel in that sense. But we studied it as a function of loading force and separation, so you can do a full AFM scan, or you could have a scan where the lines are separated by a certain distance. You can see, clearly you're removing more material the higher the force, and if the separation is increasing, it's not necessarily, it's getting a little bit worse if the separation is increasing. We can plot this depth as a function of force, roughness as a function of force, where roughness is a proxy for the quality of the removal of the material. And also we can plot this, we can do this experiment as a function of tip velocity, how fast the tip is moving for particular separations. So for the most part, we don't see a very strong tip velocity effect. Of course, the force is a very key parameter. The higher the force, the more you remove. And there are different regimes. So there's a plowing regime and kind of a polishing regime. Plowing, you're actually removing the material. Polishing would be more suitable for tomographic approaches where you don't want to damage the layer that you're trying to image the functional property of. We tried fitting it to some existing models, but the models don't take into account the presence of removed material or whether there's a structural phase change, as is in the case when you're applying micronewtons of force. For very low forces, you can see that the roughness is on the same level as the roughness of the film initially. And again, velocity doesn't play a very strong role in the range that we looked at. Okay, this wasn't recorded simultaneously. It was recorded after the fact, but in principle, you could be measuring current as you're doing the measurement. So the diamond tips are doped, so you could be removing material, measuring current as an indication or even a feedback of when you've reached the film, or you start to even sense the layer underneath if you don't want to go through the film. So that's also shown here. So at the time we hadn't had TEM of this, so we didn't actually know the film thickness precisely, and so this correlates what we saw around 50 nanometers is when we start seeing conductivity. Okay, and I'm kind of cheating because I'm not showing you how the sausage is made. This is what it looks like after doing the routine. So the debris is there, and then we have to have a separate cleaning step, so we have to remove that. So we remove it by imaging with a low force. It looks like that. If we do a slightly larger area, you'll see that we push the debris away. So now it's all around the edge. We didn't try this. You might be able to clean this by some sonication or something, but this was the approach that we used. So machining with the forces that we wanted, then cleaning with a low force that we would normally use for contact mode imaging anyways for doing PFM, and then having a nice clean area. And we were worried, and certainly with some metals, we did have a problem where this would just go back inside the trench that we filmed, that we machined. So the material property is very important. Okay, so we were interested in trying to understand what's the smallest structure we could carve. So to do that, since this is a 50 nanometer film and we didn't think we could carve a completely isolated structure, we just wanted to carve a kind of a surface structure. We wanted to see what's the deepest, narrowest line we could draw. And then if you can draw two deep, narrow lines adjacent to each other, that's going to limit the size that you can, size of the structure you can make. This is a little time consuming, so it's drawing a circle, taking the sample out, rotating it, putting it back in, and understanding both if there's an influence of the substrate or the crystallography. And then what we ended up doing was seeing that, for each of these different rotations, you can see that there's a location where it looks like it's the thinnest structure. So we can plot that, and we can also monitor the tip torsion, the lateral deflection while we're doing this. And you can see that the lateral deflection is close to zero, both at around 0 degrees and around 180 degrees. So for a 0 degree scan, that's going to give you the narrowest structure, as indicated here by the half cone angle. So we can do cross sections and look and see what is the actual half cone angle for these trenches that we've drawn, where the thinnest part would be the smallest angle. And this can be improved just by using a stiffer lever. So if you improve the stiffness so that the lateral stiffness is higher, more comparable to the normal stiffness, the tip won't twist as it's going around and carving this structure. But for the rest of the work, then, we only carve in that direction. So we're going to carve a very small structure, and what we do is take the sample and rotate it, so all the lines we draw, all the cuts, are with this 0 degree scan. Okay, so now that we know we want to do small lines, we varied the force and the tip velocity again. The tip velocity, again, didn't play a strong role, but the force, of course, does. So this is going to tell us what tip velocity we should use and what force we should use if we want to make a very narrow structure. And so pulling all of this information together, kind of exploring the parameter space, allows us to then try to carve a small nanostructure, which we do here. So in the end, this is around 90 nanometers in size. You can see this kind of hashtag, which of course is carved with rotating the sample, locating the spot again. With a stiffer tip, you wouldn't need to do that to have the same structure. And fortunately, it remained ferroelectric. It still switched. Maybe the hysteresis loop doesn't look as nice, but we were able to switch it as though it retained the ferroelectricity. Comparing, again, the film with a couple of different nano islands, you can see that we are kind of, it's not a statistical approach, it's a couple of examples, but we've lost that symmetry a little bit, and it looks like the coercive field has changed, maybe even some more imprint. So it's something to keep an eye on in terms of understanding what the limitations are. But we tried a variety of different things. We were hoping to see maybe a size effect, right? We released the strain, we started to see different switching behaviors. I was looking at this in preparing the slides, and so we carved different size structures, and if you look at this 500 nanometer line going down to the 4 micron, it looks like there is a change in this coercive field that might be worth exploring more in the future. Well, yeah, we tried a lot of different things, a lot of different structures. Here's another example of a nano island that we carved, and yeah, a variety of structures, leading to a nice fabricated nanoray, a nice example of lithography, and this is a single pass. So I was surprised how well this worked. For other materials, it doesn't work this nicely. We've looked at lithium niobate and some other materials. If it's brittle, you can end up fracturing and getting cracks. But for the right material and the right force, the right regime, you can get these nice structures. We wanted to see if we could carve metallic electrodes. So again, this isn't carving all the way through the material, it's just carving the metal on the surface and maybe a little bit deeper. But delamination was a problem. So trying to fine-tune and optimize that was a challenge. But this was the best that we got, so there's at least some metal left on all of these elements, and every element was switchable, as shown here. Here's a 3D representation of the phase map. We switch it into a checkerboard structure and switch it back. So fortunately, it does retain the ferroelectricity. I think there's some promising avenues here where we can carve structures and we can carve electrodes. We can do it in the same system. So we can, in principle, make some more exotic structures that would be very challenging for labs without focused ion beam to do, and maybe without the need to deal with the ion implantation. Another striking thing, for me anyways, is that this is a reconstruction of the tip from the very beginning. And the only change that we saw in these tips was after the first scan or the first attempt, and after that it was very stable. So most of the deterioration happened very early on. We used basically 2 tips for all of the work here. One was for carving sharp structures, where this is just 2 or 3 nanometers, and the other one was a 50 nanometer tip apex for removing a lot of material. That one didn't change at all. This one changed only slightly. So even though the tips might be more expensive than other tips, they really can last quite a long time. So the basic summary here is that we can apply a force with an AFM tip to both image, right, to do regular PFM, to induce a structural phase change through the application of the force. We can change the switching current. We can change the coercive field. We can do machining to make a variety of different structures. In ferroelectric films, you have to kind of optimize it for the material that you're looking at. We were able to retain the ferroelectricity in these nanostructures that we carved, and the parameters can be checked by the same method that we used here. So yeah, again, this work was in collaboration with colleagues in China, the US, and Northern Ireland. And this is my group at UCD, and when we published this machining paper, we did put up a couple of the logos. Again, it's just loading an image file, and just in one pass, it carves the structures. So I'd be happy to answer any questions.
Okay. Yeah, thank you very much. And questions, please?
Thank you very much. For the first part with the dead layer, did you do similar experiments with a top metallic electrode and to compare if you still have this kind of dead layer as well?
We didn't look to see if we still had the dead layer or the effect of the dead layer. That's where the two works kind of combine, but we hadn't done it. We were limited a little bit by reduced access to the lab in the end of her PhD. But that would be.
And for the dead layer itself, how did you identify this dead layer? Because with TEM or with?
So yeah, I showed a TEM image, but I wouldn't have been the one that identified it. So our co-authors would have identified it from TEM. But the dead layer has been reported to exist in similar thin films, BFO films of this thickness.
Okay.
Very nice work. So I would love to have that something like 15 years ago when you've been at Max Planck. So anyway, do you, how reliable is in terms of force, velocity, or whatever parameters and material? So let's see, if I would know that I want to remove or make a ridge of 10 nanometers in the material, if I'm giving the right parameter, is it going to get there?
Yeah, I don't know. So we didn't really look at the reproducibility so much, but in the cases where we had nanoarrays, that's doing sequential lines. So the tip does one line, then lifts up and comes and does another line. The spacing was very regular, I'd say. It's not quantified. The challenge would be if the tip is, if the tip geometry is changing over time, and it wasn't changing over time, or if the AFM has a closed loop scanner or not. I did find that if I would do a structure, so that's kind of loaded with a lithography, you draw the lines and that's where you want it to go. If I would to try to do another one on top of that old pattern, in that case, it didn't always line up, but that's more of an AFM issue. And perhaps you noticed that when I was doing the scanning, when we were doing the scan angle study, it wasn't always along zero that was the best. It was a little bit off zero. So that could be because basically the material has to fracture, it has to break a little bit. And when that's happening, there's a little bit of twisting. So the tip is going in a certain direction. There's the possibility also of a slight offset in terms of placing the cantilever. It's not always perfect. But we did notice that the tip tends to move in a certain direction at the beginning. And that shows up in that. But also one thing I should point out is we put that same tip reconstruction in the trenches that we drew. And the tip is so narrow compared to the trench. Like there's room for significant improvement. And basically it comes down to how the material breaks for the forces that you're applying. And we were fracturing the BFO and we were creating a much larger trench than the thickness, than the width of the tip. So getting the right material. And we used metal electrodes, but using transparent conducting electrodes like we use for the bottom electrode, that's a really good way forward in this, because then the mechanical properties are somewhat similar in terms of machining.
So you didn't try any lubricant or something?
No, but that's something for future work. So what we see with regular diamond tool machining is they vary the bias, they vary the temperature, they use coolants, they have water. There's a lot that we can do, and we can recreate in an AFM environment.
Yeah, okay, other questions?
Brian, when you show machined ferroelectrics, I think it was slide 24, there were loops. Okay, so do you think that this asymmetry, so some of the loops are asymmetrical, meaning that D33 in one direction is weaker than in the other? Do you think it's genuine asymmetry, or it is, or it really represents the presence of some secondary phase or something?
Yeah, it's a good question. It's hard to really know, and we didn't apply in this case mapping of switching loops. So we didn't use BEPS or anything like that to see really if there's a variation in the switching properties across. Also associated with machining and removal of material, there can be a damaged layer that's reported in regular machining processes. So it could be that the quality has changed, or there's a structural phase difference there as well.
Because in the normal ferroelectric, there shouldn't be a difference between orientation up and down, right?
Yeah, yeah,
So-
and the shape is, no, it's not, so it's not completely isolated from the film, and the shape isn't square, it's following the shape of the tip or what's left over after it broke off.
And the second question, so if I understood correctly, so your interpretation suggests that you heavily squeeze your dead layer, and consequently you have high tunneling current. It's like this?
Yeah, so I probably missed a step in the explanation. So yeah, I think we're squeezing the dead layer, which allows for injection of charge, and at the point where you're switching, that charge can be transferred across. So because of the screening, the need for the screening at the time you're switching. And I think that's what's resulting in that enhanced current.
And looking at the difference in the amplitude, you have to squeeze it quite a bit.
Yeah, actually, so yeah, we had to squeeze it quite a bit. The forces were relatively high. But if we look at the amplitude of the loops, the amplitude is increasing increasing with force. So the response is getting higher, even though we're pushing harder. So that goes along with the fact that we think we're squeezing the dead layer, because more of the voltage then is going to the ferroelectric.
D33 is getting high, or just the resonance is higher?
We're only looking at effective D33, yeah. Okay. So that's getting higher in our amplitude loops when we're doing the measurement. So it's consistent with the idea that we're squeezing the dead layer, and so more voltage is going across the ferroelectric.
Thanks.
Yeah, I want to, it may be too late, but I have also a remark about this dead layer. So what is this dead layer? Is it a different, dissimilar material, or is just the material itself that has no ferroelectricity? Because in the second case, when you apply a force, maybe this material becomes somehow ferroelectric and,
Yeah, so I can't know for certain. I don't know what happens to the dead layer itself when we apply a force. We treated it as a similar dielectric material that doesn't switch.
With the same composition, more or less.
Yeah.
Okay, so it's the same material at the end. The dead layer is the same material.
But
it's not a contamination.
I don't know if it's changing as we're pushing. We see that it's quite complicated. That as you're pushing on the material,
okay.
Are you making your measurements in air or in vacuum?
These measurements are in air. Yes.
So maybe it's water on the surface?
Yeah, that's one thing that we didn't look into yet. So there could be that as you're pushing, you're changing the charge configuration and you're causing dissociation of water. As you're pushing, it could be the equivalent, it is the equivalent of applying a bias. It could be causing oxygen vacancy migration, right? There's a lot that's going on, but the oxygen vacancy migration, it would only go in one direction, again, just like the flexoelectric effect. And as soon as we remove the force, it goes back to where it was, and it wouldn't be staying in a stable state.
But then it's simple, you just repeat the same experiment in vacuum.
Yeah, we can do it in vacuum, we can do it under a more controlled environment, limited to what we have access to.
Or in argon or something.
Yeah.
Okay, anyone?
If I understood correctly, you are dumping tens of micronewtons on a basically 25 nanometer square area. So the pressure is huge.
Yeah.
So have you considered the possibility that the increasing conductivity is due to the fact that you're pushing bismuth ferrite towards a more conductive state, towards a bulk more conductive state? No, so it's nothing to do with a dead layer, but the fact that you're approaching. Bismuth ferrite is reported to have a metallic state at high temperatures, so presumably also at high pressures.
Yeah, no, that's a good point. I mean, it's similar to the idea that the barrier is being reduced between the ferroelectric states. I wasn't sure how to probe it exactly in our experiment.
Okay.
But yeah, I think we don't rule that out. It could just be becoming more conductive because it's easier to switch in both directions, and it'd be interesting to see if the same trend is observed in other materials that might not be higher conductive.
Okay.
But the fact that the bismuth ferrite is multiferroic influences somehow this finding. Is there any difference if you just try to do it on a normal ferroelectric with respect to the bismuth ferrite?
Yeah, it's
some magnetostriction.
We faced this challenge from the beginning. I'm not sure why we necessarily chose this film to do the work on. It's basically what we had access to, but it doesn't make sense from several points, right? We should have started with something more standard. We have both the mixed phase transition. So it does become quite complicated. It's difficult to pinpoint everything. So at 400 nanonewtons, which is happening every time we're doing the machining, say, we are having that structural phase transition. At the structural phase transition, we're probably having a rosette of conducting domain walls and phase boundaries that might have different properties. And that's all happening under the tip and may not be visible. So there's several different factors, I think, that are going on. But yeah, applying this to other materials, I think, is a worthwhile avenue.
Did you look at the regular R-phase BFO instead of using the morphotropic phase boundary?
No, we only looked at the morphotropic phase boundary, these mixed RT phases.
Okay.
They were the samples we had from our collaborator.
Okay.
Thank you. Did you see significant increase of leakage with the stress?
Yeah, so the higher the force we applied, the more leakage we saw, but it wasn't completely in line with the force that we applied. The leakage happened at a different voltage than the switching currents, but yeah, there was more leakage associated with higher forces. So there's something to be said for a better electrical contact as well, and a larger contact area as we're pushing into the material.
Okay, I think we can continue during the next coffee break, so thank you once more. And thank you to all the speakers from this session, and okay, the session is closed.